Hi, everybody, and welcome to Chapter 20. Okay, so Chapter 20 and Chapter 19 are very, very similar. So biggest difference here is that we are going to be looking at carboxylic acids and their derivatives. This is a different class than aldehydes and ketones, primarily because when we look at carboxylic acids and their derivatives, we do not have hydrogen or carbon groups on both sides of the carbonyl. We have oxygen groups, nitrogen groups, or halogen groups. And so those are going to be in a different class because they're what we are going to call leaving group carbonyls. And we'll see why in these reactions, instead of nucleophilic addition to the carbonyl, we will actually be seeing nucleophilic substitution reactions. Let's go ahead and get started. Now, just as an introduction to the carboxylic acid, we see that they are very abundant in nature and they can be found in a wide variety of synthetic pharmaceuticals. Acetic acid, butanoic acid, all the way down to acetylsalicylic acid, which is aspirin. So looking at all of these carboxylic acids in nature, we see them not only used in nature, but also in pharmacy. So the U.S. produces over 2.5 million tons of acetic acid per year. Acetic acid is household vinegar, and so it's primarily used to produce vanillin acetate. The vinyl acetate is then used in paints and adhesives, but acetic acid also is something that we probably are very familiar with. Vinyl acetate is an ester. And that is what we are going to call one of our carboxylic acid derivatives, right? The carboxylic acid itself has the OH group. If this group is slightly different, but is still classified as a leaving group carbonyl, it is called a derivative of carboxylic acid. Again, when we're looking at the structure and properties of carboxylic acids, trigonoplanar is our geometry. The actual carboxylic acid is capable of hydrogen bonding. And so we see that dimers tend to form for carboxylic acids, which we have talked about a little bit before in terms of in the IR spectroscopy chapter, when we talk about why is the carboxylic acid OH stretching so broad that it goes past upfield of the 3,000-2,800 mark. The hydrogen bonding also accounts for why carboxylic acids have higher boiling points than alcohols. So what we want to remember is that carboxylic acids are weak acids. They have a pKa around 4 to 6. I put the pKa of acetic acid there, 4.75. So they exist as weak acids, and they actually can exist as a carboxylate salt in the presence of a base. So a base can come in like hydroxide and deprotonate. And the reason why that oxygen to hydrogen bond is so much more reactive than the OH bond of a normal acid, such as that in water, is because of the resonance that is hanging out there in the product, right? So the carboxylate salt is resonance stabilized, which means that it is more stable than hydroxide or other OH minus ones. And so when we're looking at the equilibrium of the carboxylic acid and carboxylate at physiological pH, if we think about the acid and the conjugate acting as a buffer, we remember the Henderson-Hasselbalch equation a little bit. At physiological pH, which is 7.3, the ratio of carboxylate ion to the corresponding carboxylic acid is 1,000 to 1, meaning 1,000 more times the base than the acid itself. Okay, so the carboxylate ion is very stable. One example of this buffer in our human bodies is pyruvic acid, which exists primarily as the pyruvate ion in physiological pH. Carboxylate ions and their role in biology is covered in chapter 5, which we will not be working with, but it's just nice to know that we do have our own carboxylic acids in our body, and they have buffering capabilities because they are weak acids and can exist as a weak acid with its conjugate in solution. Another a good example is the blood buffer that we have, right? Carbonic acid with bicarbonate. All right, we do know quite a few ways to prepare carboxylic acids. You should recall these if you have any issues with remembering. The section numbers, again, are present for you. We can do oxidative cleavage, which is ozonolysis of alkynes. The triple bond gets completely broken, and what gets placed there across that triple bond are carboxylic acids. If you have a primary alcohol and you use a strong oxidizing agent, such as sodium dichromate, chromic acid oxidation reacts that primary alcohol and removes both of those alpha hydrogens to create a carboxylic acid. And from chapter 17, which may be a little bit more recent than the other two, taking any benzylic position, as long as that benzylic position has one hydrogen, at least one, right? Remember, has to have at least one hydrogen on that benzylic position. Sodium dichromate will oxidize that benzylic position to become a carboxylic acid. We also saw hydrolysis of nitriles last chapter. This hydrolysis of nitriles, taking the carbon triple bonded to the nitrogen, adding H3O plus and heat to make it a carboxylic acid, is a great way to add on the carbon, right? It's a synthetic step we used last chapter to increase the number of carbons in our molecule. And it's also a great reagent simply because we know this SN2 reaction from last semester with that nitrile, the cyanide ion, Cn-1, can come in and do a backside attack on a primary alkyl halide, and then H3O plus will convert that carbon to a carboxylic acid. Great synthetic step. Carboxylation of a Grignard with CO2. This is something relatively new. So we know Grignard reagents, right? Grignard reagents were the ones where we had some sort of R group attached to a magnesium bromide. And that R group specifically had a lone pair with a minus charge because magnesium is a metal. So it will be the cation in that ionic bond, and the R group will be the anion, which means the R group, again, is a nucleophile, right? This was our nucleophile of Grignards from last chapter. Well, what is really awesome about these Grignard reagents is we can actually add them to carbon dioxide. Now let's look at this reaction. When that nucleophile attacks the carbon of carbon dioxide, it kicks up one of the carbon-oxygen pi bonds. Doesn't matter which one, they're the same. And it makes the carboxylate ion. You follow it up with an H3O workup, H3O plus workup, and you get a carboxylic acid. Notice that this would be step 1. This is step 2. All right, so the acid workup is a subsequent step, and it is necessary. I'll show you an example in just a second. It is necessary as with any Grignard reagent to make sure that we wash, right, the solution. So this gives us a second method to convert an alkyl halide into a carboxylic acid in a 2-step synthesis. First one, using the nitrile and hydrolysis. Second one, prepare a Grignard and then react it with carbon dioxide and H3O plus. All right. Carboxylic acids can be reduced to a primary alcohol with lithium aluminum hydride. This is our hydride reagent. We're going to go through this reaction a little bit quicker. So LAH is a very strong base. So the first thing that it does is actually deprotonates the carboxylic acid. We do not use hydride to attack the carbon of the carbonyl because that nucleophilic attack is not as easy as a proton transfer. Right there. The carboxylate ion is formed. It is very stable. This produces H2 gas, which bubbles out of solution. Le Chatelier says that's fine indeed. And then with aluminum trihydride, we actually can reduce the carboxylate to an aldehyde. So the first thing that happens is the hydride will attach to the carbon, and that causes the pi bond, squeeze it over there, to attach to the aluminum. Those dotted lines are just there to show you the coordination of the aluminum to the oxygen, which is a very good bond to be formed, and then the hydrogen or the hydride, H-1, to the carbon electrophile. And then our oxygen coordinated to the aluminum can be kicked out, all right? And so the aldehyde is formed. This oxygen of the carboxylate is the one that is going to become the oxygen of the carbonyl, okay? And then the aldehyde is reduced to a primary alcohol, just as we had done before, where hydride now can attack the carbon of the carbonyl, kicking up a lone pair. There's no ability to proton transfer. There's no acidic proton in aldehydes. And then the H3O workup, which comes after, will be our proton source to protonate the alcohol itself. BH3 can also be used instead of lithium aluminum hydride. It's chemoselective for a carboxylic acid. So BH3 and THF will only reduce carboxylic acids. That's what chemoselective means. It is selective to this specific functional group only. If you remember, LAH reduces everything. It reduces all pi bonds. In reality, we're going to be dealing with the carbon oxygen ones. However, BH3 is only going to be able to reduce a carboxylic acid to a primary alcohol. So that's super great indeed. You can see this example here. We have a ketone on one side of our molecule and a carboxylic acid on the other. By using BH3 and THF, we only reduce that carboxylic acid, not the ketone.